Okay, so let us now push on to question 87. So, an alarm at a fire station rings and an 86-kilo fireman, starting from rest, slides down the pole to the floor below. So the distance is 4 meters. So just before landing, his speed is 1.4 meters per second. What is the magnitude of the kinetic frictional force exerted on the fireman as he slides down the pole? Okay, so this is quite interesting because we are given a lot of sort of kinematic values, but we are also told we want the kinematic frictional force. So that's going to be our friction with K. So kinetic friction is the coefficient times the force normal. Okay, so the big thing here is we need to know how much friction is being exerted from the pole onto the fireman. So what I'm going to do is, so this is our pole and I'm going to label our axis. So for the purposes of this question, I'm going to say that upwards is positive and downwards is negative. So then I ask myself, okay, what forces are moving upwards and what forces are moving downwards? So the fireman is jumping and sliding down the pole. So what causes the fireman to slide down the pole? It's obviously gravity, so due to his weight. So the force that is pushing him downwards is going to be mg, mass times gravity. So what forces are working up here? What forces are pushing him upwards? So this is obviously the force that's slowing him down, which is going to be kinetic friction. Okay, so we've got some direction here. We've got some values. So what I'm going to do is now we're going to have a look. Let's see what values we're given. So we know the mass. We're given his mass, which is 86 kilos. Now he's starting from rest. So the initial velocity is going to be 0. We know that his final velocity is going to be 1.4. Now the magnitude of the kinetic friction, we don't know, so this is what we want. So what is the magnitude of the kinetic frictional force? So this is what we want up here. So I look here and I go, okay, so the frictional or the force of friction is going to be the coefficient of friction times force normal. So I don't have the coefficient of friction, and there's no way for me to really calculate that. However, I do know the change in his acceleration. I know the change in his overall velocity. So what I can do is, I know that the force that he is moving downwards is mass times gravity. So that means that the force going downwards is going to be 86 kilograms multiplied by 9.8 meters per second squared. So that means that the force going downwards is going to be 842.8 newtons. So we have 842.8 newtons screaming down. Another thing too is we can see a bit of kinematic stuff here and we sort of sit back and go, well, okay, what are we supposed to do with it? What's the link? So what is the question asking for? Well, it's asking for a force. And we go, okay, that's fine. How do we find a force with this? So we look for the common link. And the common link here is going to be acceleration. Because we know that force is equal to mass times acceleration. And we have enough here to calculate the acceleration. So we can go v squared is equal to VO squared plus 2AX. So his final velocity is going to be 1.4 meters per second squared is equal to VO squared. So the initial velocity, which is going to be 0, plus 2AX. So 2 times A, which is the acceleration, which we don't know, and the displacement. So the displacement is going to be negative 4 meters. So why is it negative 4 meters, I may hear you ask? And that is because, remember, we set our direction. So we are starting from here, we're finishing here. So we're moving towards this negative here. So because we set it that everything moving down is going to be negative, we is moving in negative 4 meters. So we rearrange our formula here. So we're going to have 1.4 meters per second squared divided by, so some multiply, so 2, and a multiply, so this is going to be multiplied by negative 4.0 is equal to the acceleration. So the acceleration is going to be, so 1.4 times 1.4 is going to be 1.96 divided by 2 times negative 4, so it's going to be divided by negative 8, which means our acceleration is going to equal to negative 0.245 meters per second squared. So what this means is that the fireman is going to be accelerating at 0.245 meters per second squared this direction. So now that we have our acceleration, we can now move on to calculate the total amount of force. So we know the total force is going to equal to the mass, which is 86 kilos, multiplied by the acceleration, which is going to be negative 0.245 meters per second squared. So 86 times negative 0.245, the total force is going to be negative 21.07. What we do now is we can see that if the fireman was just to jump down, okay, if he was to just not even grab the pole and just free fall and go splat, he would have a total force, a total downward force of 842.8 newtons. However, what we've calculated here is, judging by his initial and final velocity and looking at his acceleration, he only had 21.07 newtons. So, why is it that he only had 21.07 instead of 842? It's because friction was working in the opposite direction to counteract that net force. So we know that we had 842.8 newtons. So that's how much force would be plummeting down this way if the fireman never grabbed the pole. Now we know too that because he did grab that pole, the difference here is 21.07 newtons. So that's how much force he actually had coming down, meaning that the overall result, so the kinetic friction, so how much friction was actually imposed, was 821.7 newtons. So, a quick recap. Again, what we've done here is we calculated how much force the fireman was jumping down with. So, theoretical. We then calculated how much force he actually jumped down with, and we could see the difference, which was thanks to the kinetic friction. Okay, so let us now look at question 99. So, a student presses a book between his hands. Okay. So the forces that he exerts on the front and back covers of the book are perpendicular to the book and are horizontal. That's just a really, really unnecessarily complicated way of saying he's pushing the books in here. Okay? They're horizontal and it's perpendicular to the book. So the book is here, it's perpendicular, so it's pushing this way. So the book weighs 31 newtons. Okay, so that's interesting. The coefficient of static friction between his hands and the book is 0.4. Okay, so again, we've got a value here, the coefficient of static friction. So that's giving us a point in the right direction. To keep the book from falling, what must the magnitude of the minimum pressing force that each hand must exert? Okay, so we have our book here. We're essentially holding it up like this. So how much force must each hand apply to this book to stop it from falling through? big thing here is we are told the coefficient of static friction. So I'm going to write static friction is equal to the coefficient of friction times force normal. Now, the force normal here is always perpendicular to the friction. So the friction, so if we're holding our hands onto the book like this, so that means the friction is going to be working this way. So perpendicular, that means the force normal is going to be our pressing force. Now, we are also told that the weight of the book is 31 newtons. And also, something we can see from this as well is that what is causing this book to stay, in our hands is due to the static frictional force. So that means that the amount of frictional force is what's holding this book up. But the key thing here is, where are we seeing friction? We are seeing friction on both of our hands. Because we can't just hold it up with one hand, we need both hands. So it's the static friction from both hands that is holding up our book. So what we can see here is that the total static force, so the static force due to friction, is going to be equal to the weight of this book. Because again, there is no net motion. We want it to remain still. We're not going to have it floating in the air or sort of have it sliding down our hand. We want it to remain stationary. So we know the force here is going to equal to the weight. The big thing here is that we're not holding it by one hand, we're holding it by two. So this means that our static friction, which is equal to the coefficient of static friction times the force normal, that's going to be multiplied by 2. So we know that 2 lots of static friction is going to equal to the weight. And we know that each of these static frictions is going to be this. So I'm going to multiply this by 2 and substitute it into our formula here. So that means that our frictional force is going to be 2 times the coefficient times force normal. So we're going to have 2 lots of coefficient times force normal. It's going to equal to the weight. And that is the formula that we're going to use, this one here. So the biggest thing is we need to solve for our force normal. So now it's just simply a matter of rearranging and solving our little equation here. So because we want the force normal, we can rearrange this here. So we can move the 2 over and we can move our coefficient over. So we're going to have the force normal is equal to W divided by 2 times the coefficient of the static friction. So force normal is going to equal to the weight, so the book weighed 31 newtons, divided by 2 times the coefficient, which is going to be 0.4. So 2 times 0.4 is 0.8. So 31 divided by 0.8 is going to give us 39 newtons. So that means that we have to press that book with a force of 39 newtons in order to create enough static friction to stop it from slipping through our hands and falling on the ground. And that is our final answer. Okay, so let us look now at page 109, question 104. So, when a 58-gram tennis ball is served, okay, so it accelerates from rest to a speed of 45 meters per second. Okay. Now, the impact with the racket gives the ball a constant acceleration over a distance of 44 centimeters. Okay, so what is the magnitude of the net force acting on the ball? So we want to know the total force that is acting on the tennis ball. Now, we were given a lot of key information here, so we were told the mass. So the mass of the tennis ball is going to be 58 grams. Now we can see that it accelerates from rest. So our initial velocity is going to be 0 meters per second to a speed of 45. So our final velocity is going to be 45 meters per second. Now, it gives a constant acceleration, so that should spring to mind. Constant acceleration, kinematic formulas. Over a distance of 44 centimeters. Okay, so x is equal to 44 centimeters. What is the magnitude of the net force? So, again, I'm seeing kinematic formulas, I'm seeing constant acceleration, and I'm seeing force. So one thing that's jumping the mind is F equals ma. But, so we're given the mass, we need the acceleration. Now, there is absolutely no mention about time in this entire question. So I'm going to use the equation v squared is equal to VO squared plus 2ax. Now I'm going to rearrange this to isolate the acceleration. So this is an addition, so it's going to turn into a subtraction. So v squared minus VO squared. The 2 and the a multiplied, and the a and the x are multiplied, so they're going to turn into a divide. So it's going to be divided by 2 times x, and that's going to give us our acceleration. Now, we just simply need to plug and chug. So what we do is, we go our final velocity. So the final velocity was minus the initial velocity, which is 0, so we don't need to worry about that, divided by 2 times x, so 2 times the displacement, but it's given to us in centimeters. So we need to be careful here because this is a trap, because displacement is in meters. So we need to convert this into meters. So 1 meter is equal to 100 centimeters. So this would give us a total meters, so we convert this by moving the decimal point, meaning that our total displacement is 2 times 0.44 meters is equal to acceleration. So you pop this into your calculator, so 45 squared divided by 0.88, and that will give you an acceleration of 2,301 meters per second squared. So this thing is accelerating at an incredibly fast rate. So we have our acceleration. We know our mass from over here. So now we can solve for the total net force. So the total net force is going to equal to the mass, which is 58 grams. But again, the mass here of this force is in units of kilogram. So we need to convert this into kilograms. So we're going to have 0.058 kilograms multiplied by the acceleration, which is going to be 2,301 meters per second squared. So we multiply these two values together, and we're going to get a total net force of 133.47 newtons. So that one was actually a nice simple one. It looks very confusing, but if you're able to integrate and fuse those kinematic equations and how to work those with forces and looking at the overall motion of something. So ask yourself, is it moving? If yes, why? What is making it move? And that will help you deduce the answer. Okay guys, so that now finishes Module 13 Video 2. So thank you very much for joining me today. I hope you all enjoyed it. If you do have any questions, queries, suggestions, ideas, anything like that, please feel free to email me at b.grant@griffith.edu.au. So just quick reminder again, please don't forget to do the surveys. Really does help me out a lot. So we're near the end. So keep up the hard work, guys. Okay, end of semesters are creeping up. So keep working hard, stay focused, and I'll see you guys next time.